This lecture is about guided mode resonance, which seems to be all the rage these days and goes by many names. Sometimes you'll hear it called high contrast gratings, planar photonic crystal slabs, guided mode resonance, leaky wave devices, many names, but we're talking about the same phenomenon. In this lecture, we will learn that there's two physical mechanisms at work to produce what's called a guided mode resonance, and that is diffraction and waveguiding in a slab. So we'll talk about those, then we'll combine those concepts and talk about what guided mode resonance is, and then discuss their use as filters. We'll then go into designing GMR filters and all the different aspects of what affects their performance, what effect it has, how we can make them polarization independent, and things like that. And I'll end with a few samples of how these things are being applied. First topic is slab waveguides. Remember, we have something called a critical angle. If we have a wave going from a high index medium into a low index medium, we know at the interface that it will refract and it will also reflect. There's a very special angle right at this dashed red line, such that if we're incident at a larger angle, we will get no transmitted wave. We will only get a reflected wave. There certainly is a bit of a temporary surface or evanescent field, but that eventually leaks out in terms of this reflected wave. So 100% of the power gets reflected for all angles greater than this critical angle. And we can calculate the critical angle just giving the two different refractive indices. Where here N2 is the lower refractive index and N1 is the higher refractive index. Just to give you an idea, the critical angle going from glass to air is about 42 degrees. So based on this critical angle, when our wave totally reflects, we call that total internal reflection. Now suppose we have a medium with high refractive index surrounded by two different materials, potentially different, where both of the refractive indices of N1 and N3 are lower than N2. That means we will get potential for two total internal reflections. And in fact, a ray could stay trapped in this medium. We call this a slab waveguide. And by slab waveguide, we're really talking about something that's infinite extent in the plane of the guide, but finite in that vertical direction. If we trace that ray and we look at this point and then the next point where that happens, it turns out the phase between these 2 points has to be an integer multiple of 2 pi. If that is not the case, that does not correspond to a guided mode, and in fact it would leak out of the guide. But because this condition has to be met, there are only discrete rays that can propagate in the guide. So what we've built up is sort of the ray tracing, hand waving argument of why we only have discrete modes in a waveguide. But given the angle of that ray, we can calculate its propagation constant. It's just the free space wave number times the effective refractive index times the angle of that ray. And the refractive index times the angle of the array can be lumped together in the effective refractive index of the mode. In reality, particularly for small waveguides, it's not the best to look at this completely in terms of a ray tracing picture. That's good for a qualitative description, but in fact this does need to be analyzed rigorously with Maxwell's equations. So we would set up a problem something like this. We draw our slab waveguide, we'll let the direction of propagation be z, and we'll have the cross section of the guide in the xy plane. Then, using techniques we discussed last semester, we could calculate the modes that exist in that guide. And here's what they look like. For this particular slab, the first 5 modes, maybe I designed this so that there's only 5 modes, not sure. But here's what the modes typically look like. Starting at the right with the fundamental mode, it has 1 hump. The second order mode has 2 humps. Third order mode has 3 humps, and so on. And we can think of this first order mode as 2 waves traveling at a very, very shallow glancing angle. And as we go to the higher and higher order modes, we're talking about rays that are bouncing back and forth between the interfaces at much larger angles. So that's everything we need to know about slab waveguides. On to the second concept of a guided mode resonance device, and that's diffraction from gratings. So we've discussed this at length in previous lectures, but just to remind you, anytime we have a field or a wave propagating through something that is periodic, that wave takes on the same periodicity as what it is propagating through. So the grating essentially chops up the wavefront, making it periodic. Anything that's periodic we can decompose into a Fourier series. Now our wave is really the sum of discrete things, and those discrete things are plane waves and evanescent modes propagating at different angles. And so the possible angles that we can have given the period of our device and wavelength is quantified by the grating equation. And we would write it slightly differently depending where we're looking. We would change out this first refractive index for the refractive index on the top of the grating if we're looking at the diffracted modes up here in the reflection region. Likewise, if we're looking for the directions in the transmission region, we'll make that the refractive index of the transmission region. Otherwise, the equation stays the same, remains unchanged. Now we'll pull these together and talk about what a guided mode resonance device is. We have at the same time and in close proximity both a grating and a waveguide. The picture I'm showing here shows the grating and waveguide separate. In fact, the grating could be inside the waveguide, underneath, or really in any combination. They just have to be close enough that they're electromagnetically coupled. So we have an incoming wave, and it sees a grating and is diffracted into these multiple modes. Well, we know from the ray tracing picture it is possible that one of these could be a supported mode, a guided mode. And so there's the possibility then that we can diffract an external wave and couple that into a guided mode. So this really goes back to our discussion in coupled mode theory, how we can couple an external wave into a guided mode, and also our discussion of gratings. So this is happening at the same time. Now likewise, as that mode is now propagating through the waveguide, it also sees the grating, and that grating makes it slowly leak back out. That's required by reciprocity. We couple a wave in, the wave also couples back out. So when this condition is met, when we diffract an external wave into a guided mode, that's guided mode resonance. Here's pictures to give you a feel of what's happening. If we're not on the resonance, we are not diffracting into that special angle that would become a guided mode along the slab, and this really just acts like a slab with an average refractive index. And if we look at the field passing through this, we see maybe there's a little bump or something happening here, but for the most part we just see a plane wave passing through. Likewise, when we're on resonance, we couple an external wave into a guided mode, and as that's being guided, it is slowly leaking out. And it's the interference between this leaked wave or the outcoupled wave and the applied wave that produces a filter response. So if we look at the field on resonance, we don't see it because it's washed out in the background, but there is certainly a plane wave incident on this. It excites a guided mode, and what you're looking at is a guided mode that's maybe 10 or 20 times more intense than the applied wave. That's why, because of the color scale here, we don't see the wave escaping or the wave coming in. We just see the guided mode. If we plotted the colors on a log scale, we would see everything. So on resonance, external wave gets coupled into a guided mode. As that's propagating, it sees the grating, it slowly leaks out, and it's the interference between the leaked wave and the applied wave that gives us a filter response. So where can a guided mode resonance device be resonant? Let's pull together two equations. First, we had our standard grating equation. That tells us the directions of the guided modes. Then we have, from our ray tracing picture, how we relate the direction of the guided mode to its effective propagation constant. So we can essentially pull these equations together and modify our grating equation so that the term on the left is just the effective refractive index. Now we have to think about conditions for guiding. Remember, it's what causes guiding in this slab is total internal reflection. That means our effective refractive index, or I'm sorry, that means the refractive index of the core has to be higher than the two refractive indices surrounding it, the cladding. Our effective refractive index has to fall somewhere between the refractive index of the core and the refractive index of the claddings. So we can bound what our effective refractive index will have to be. Well, we have this nice little expression for effective refractive index up here. We can plug that in to replace effective refractive index. And now we have an equation that tells us about where these resonances can occur. And we can plot that and we can map that. So for a rather typical guided mode resonance filter, we can plot these regions of resonance and they look like this. Now, in this diagram, we're only showing up to the third order diffracted mode, whereas in fact at the left side of the plot here, it gets really busy when we start showing fourth, fifth, sixth order modes. So it gets really, really busy down here, despite the fact that it's not being shown. What it tends to be more meaningful is these red and blue bands. So for normal incidence, the vertical axis is angle of incidence. For normal incidence, here's where our resonances can occur, and this is free space wavelength divided by the grating period. So what we see is that we would have a resonance somewhere around here for normal incidence. Well, what happens as we start coming in at an angle? So we shift from normal incidence maybe up to 10 degrees. Well, we were here, we move up. What that means is the single resonance now splits, and we actually have two possibilities of where we could have resonance. And in fact, we'll see that as we come in at an angle. We'll have a single resonance for normal incidence, and then it begins to split as we come in at an angle. Now, if we like a nice, lone, isolated resonance, we could operate here, come in at a strong angle, operate on this particular diffracted mode, and then we're far away from these other resonances. But we also see that as the wavelength gets short relative to the grating, we start diffracting into many higher order modes. A lot of busy stuff happens here. Remember, we're not even showing the fourth, fifth, sixth, seventh order modes, and all these resonances begin to overlap. Now this is sometimes not good because we have many resonances, and usually we just want a single clear, crisp filter response. But there's actually some neat things that can happen, and we'll show you that later on when we combine multiple resonances. We can use that to broaden field of view, broaden bandwidth, and do some neat engineering of the device. So why on earth would we even be interested in guided mode resonance filters? Well, at optical frequencies, metals are lossy. This is a way that we can produce a filter response that's very low loss. We can have near 100% efficiency from these. Also, what's neat, these are all dielectric. Typically, we don't get that strong of a response from a dielectric structure, but the guided mode resonance phenomenon can produce a very strong spectral response, even with just low refractive index materials. That's very unique. We can make things that are monolithic. Later in this set of slides, we'll step through the design of a completely monolithic filter. It's a slab of dielectric. We cut some grooves in it, and it's a guided mode resonance filter. So it only has one material. That makes it very robust to vibration, to shock, to thermal cycling. And if we have to combine multiple materials, they can delaminate. Maybe one will be sensitive to some kind of chemical that might be in the vicinity. So we can make very robust devices out of guided mode resonance. I think also because they're dielectric, they're potentially better for very high power beams, better than metals, where metals can arc and the loss can produce heat and stuff like that. There are some drawbacks. Compared to equivalent metallic structures, they are larger and bulkier, for sure. We're doing some research in our group to try to overcome that, and we're doing very good, and we're getting very close to actually exceeding and beating that of metals. And also compared to metallic structures, they have a rather limited field of view and bandwidth, and we're also working on that, and we're getting very close to meeting and exceeding what we can do with metals. The problem is, every time we discover something that could beat metals, well, we could also apply that concept to metals and then, in fact, beat our dielectric structures. So I don't think we'll ever beat metals, but we can get dielectrics to compete with them, and then we don't suffer the losses. So here's an array of various types of different guided mode resonance filters. We can have the basic ruled grating on top of a substrate. We can remove the substrate and have a guided mode resonance filter in air. We can have doubly periodic. We can have just some kind of surface relief grating on top of a slab waveguide that would produce guided mode resonance. We can have cross gratings. These give us polarization independence. Both polarizations at normal incidence will produce the same response. And we can have square gratings or hexagonal gratings. I like to think of guided mode resonance filters having two different responses. Away from the resonance, we have this background response. And we can design that background response either to be low reflection or high reflection. Then we introduce a grating, which will produce a resonance if it's also a waveguide. And that resonance will tend to reverse whatever transmission reflection response we have in the background. So if we have a high reflective background, the guided mode resonance filter will give us a low reflection resonance, and vice versa. So our grating, there's a number of ways we can produce that. We can produce it as bumps. We can actually build in regions with low and high refractive indices. And depending on the strength of that grating or the contrast of the refractive indices producing the grating, that will have an effect on the response of the filter. And what we can see here is we have the red response curve. This is for a very high contrast grating, has a change in refractiveness of 0.2. If we have a delta n or change in refractiveness of 0.1, we get a much narrower resonance. And in fact, we can arbitrarily narrow our resonance simply by weakening the grating, by lowering the contrast. Or if our grating's bumps and grooves, we can make them much more shallow or much more thin. But if we make the grating weaker in some way, lowering the contrast, we can narrow the resonance. And we can do this arbitrarily and make it as narrow as we want. We can't make it as wide as we want, so there is a limitation on the width. If we want to make a wideband GMR, there's other tricks that we can do, and we'll talk about that later. The guided mode resonance filter is very sensitive to angle of incidence, and we can figure that out through the grating equation. So we start with the grating equation, and maybe we want to figure out how much the resonance shifts in wavelength relative to a change in angle of incidence. So we differentiate the grating equation, and we end up with our final equation. So the sensitivity in angle, or sensitivity in wavelength to angle, is the period of the device times refractive index over m. So this says for longer period guided mode resonance filters, it will be more sensitive. If our incident region has a higher refractive index, that will be more sensitive. And the lower order the mode that we're diffracting into for our guided mode resonance, the more sensitive it will be. So to give you a typical number, we get about 6 nanometer shift in the position of the resonance for every degree angle of incidence. And so if that's not tolerable, then that dictates to you how much you have to control that angle of incidence of your wave. If that's not tolerable, then you need to do something to widen the field of view. Here's simulations, and for normal incidence, we see the blue line, we have one nice resonance. And as we mentioned before, when we come in at an angle, two things happen. The position of the resonances shift, and they also split. And what we can see is that the single resonance at normal incidence has split into two resonances. We can sort of think of the single resonance as actually being two resonances just overlapping. And then as we come in at an angle, we destroy the symmetry of the problem, and those resonances split. And they would continue to walk back and forth depending on the angle. And we just calculated that on the previous slide. So they are very sensitive to angle of incidence. They're also extremely sensitive to polarization. And this goes back to our discussion in the subwavelength gratings. There's birefringence. That grating will look like a very different dielectric constant depending on what polarization we're talking about. And that has a profound impact on the performance of the device. For example, for the E mode, we have a resonance centered at 550. If all we do is change polarization, We get the same background response, essentially the same, but our resonance jumps way over here. So polarization does have a profound effect on the sensitivity to polarization, absolutely. The other thing we could ask, we describe their guided mode resonance filter as a wave hits a grating, it diffracts, that can couple energy into a guided mode. That guided mode then propagates down the waveguide, it sees the grating and it slowly leaks out. Well, it has to leak all the way out in order for it to interfere with the applied wave. So one could ask, how long do these guided mode resonance filter devices need to be so that our performance approaches something useful, or that of an infinitely periodic device? Well, if we model this as an infinitely periodic device, here's the response we get. We get this nice clean resonance and a nice smooth background. Well, if we only had 33 periods for this particular design, we see something kind of noisy. Yeah, maybe there's something sort of happening here. By the time we get up to 66 periods, we see a lot of ripples outside our resonance, but our resonance is still a little bit ugly and weaker than it has to be. Well, as we add periods, what we see here is we get to about 200 periods, we start seeing something that I think could approximate the response of an infinite device. So the conclusion is here, we need many dozens or sometimes many hundreds of periods in order for a guided mode resonance filter to behave like a guided mode resonance filter. Now let's talk about how to design these. Here's a very, very simple way to design these. First, we forget that it's a guided mode resonance filter, and we will design something with some number of layers, and we would model this using something like transfer matrix method. And we would design the refractive indices and the thicknesses of these layers to give us whatever background response we want. Maybe we want low background reflection, maybe we want high background reflection, but we designed some number of layers, thicknesses, refractive indices to give us that. That's step one. Next, we incorporate a grating into this stack, and hopefully one of those intermediate layers has a higher dielectric constant or higher refractive index than something surrounding it, so that we also have a waveguide, because we need a waveguide and a grating. But the next thing, we introduce this grating, and we go back to that lecture where we talked about sub-wavelength gratings, and we would calculate duty cycle to realize an effective dielectric constant or an effective refractive index in that layer. So we add a grating and we pick a duty cycle so that those effective material properties match what we designed initially. At that point, the last thing we do, we maintain that duty cycle, but we adjust the period of the grating until it places a resonance exactly where we want it. That's it. That's a real simple way to design guided mode resonance filters. Here's an example. Let's say we want to design a monolithic guided mode resonance filter. So we want a slab of dielectric, and we want to cut some grooves in it and have that be a guided mode resonance filter. Well, so we start off with what's on the left. We have a two-layer problem. Layer 1 has thickness D1 and dielectric constant epsilon 1. Layer 2 has thickness D2 and dielectric constant epsilon 2. Well, we can use some kind of optimization. For this simple case, I used a function in MATLAB called least squares nonlinear, LSQ nonlin, and out comes a design. So here's one possible design. Now, if we want this to be a monolithic slab, we did constrain a few things. We can't control the dielectric constant of the bulk of our substrate. That will be whatever our material is. So that was 2.35. Now, we will be able to control the dielectric constant in this layer because we'll form some kind of grating in it, but it has to fall between air and whatever this dielectric constant is. So this one is bound. And we probably want to put some realistic limitations on how thick we'll let these layers go. But we do our optimization, and here's the design that I came out with. And this maybe isn't the only one, but it worked pretty well. It gave a pretty good low background reflection. But we have to somehow realize something with a dielectric constant of 1.1 in this top layer. So the second step now is to incorporate a grating. And we calculate the duty cycle based on our discussion from sub-wavelength gratings. And it turns out the duty cycle needs to be around 33% in order for us to get an effective dielectric constant of 1.1. So if we etch this grating in here, this device will have the same background response as our original device if we've calculated that duty cycle correctly. And then finally, the last thing we need to do is actually adjust what the period is. We'll keep the duty cycle fixed, but we adjust the period until we see a resonance at, let's say, 1.5 gigahertz. And it turned out when the period's around 6 inches, we got a resonance at around 1.5 gigahertz. So here is that device. Here's the dimensions, and here's its response. And we definitely see this low background reflection response. And when we had the period right, we put our resonance right at 1.5 gigahertz. So this is a very simple design process, and there's a lot that we can do a lot fancier. A whole other way that we're not really going to talk about here, but maybe we get a design close doing something like this, but then we use something like particle swarm optimization or genetic algorithms to fine tweak all those parameters, or even search over a broader solution space. Here's a second design example where we want to put a guided mode resonance filter on a glass substrate for optics. So our glass substrate's down here. We would model this as an infinite half space and air on top. So what we'll do is we'll design these layers, this intermediate layer, so that we get a low background reflection, or whatever background reflection we wanted. Clearly in this example we didn't do that great of a job, maybe because something with a refractive index of 2.0 is all we had, or some other sort of constraint. But anyway, this 3-layer problem gives us this background response. Then we'll go ahead and we'll take this region that has refractive index 2.0 and we'll modulate it. So we'll go a little bit below 2.0, a little bit above 2.0, and we'll adjust the period of the grating until we get a resonance right at 550. But what you'll see, notice the background response. We still see this background response, and we had to pick a duty cycle of the grating to give us that, to maintain that, and we've chosen the period of that grating to place the resonance at 550. If we change the period, we would still see basically the same background response, but this resonance now might move over this way if we went to a longer period, or it would move over this way if we went to a shorter period. So same design procedure. We design a multi-layer film, if you will, using something like transfer matrix method, so it's very fast. And then we take these layers and we turn them into gratings, but we pick duty cycles and refractive indices that give us the effective properties of our original multi-layer problem before there was a grating. Scalability is huge in guided mode resonance filters. Throughout the literature, there are wonderful devices that have been designed and optimized using things like particle swarm optimization or genetic algorithms, but they're not working at the frequency we want them to. Well, there's this wonderful property of Maxwell's equations called scalability. And if we design a device at a certain size, shown on left, so let's say this is size A, and it works at frequency F1. Well, if we double all the physical dimensions, it will behave exactly the same way, but at half the frequency, or twice the wavelength. So we can take a design that looks wonderful, but is not at the frequency we want, and scale it to put it wherever we want to. Here's an example. Let's take this monolithic guided mode resonance filter we designed previously at 1.5 gigahertz, and maybe we want this to operate at 25 gigahertz. So we can calculate a scale factor. We take 1.5 gigahertz divided by 25 gigahertz and get 0.06. If we take all of our physical dimensions and multiply by 0.06, we get a new design. Notice this looks exactly the same, except we have this background response centered, with the resonance centered at 25 gigahertz instead of 1.5. So you can scour the literature, you can find any device that has a really cool response, and in my mind, I don't even look at the frequency axis because I know I can scale those designs to operate anywhere I want them to. So here's a slide on broadband. I mentioned this, that guided mode resonance filters are really inherently a narrow band device, and also very narrow field of view. Well, the latest thing that folks have been doing for the last few years is taking a multiply resonant device and moving those resonances rather close and producing an overall broad frequency response. So what we see here is reflection and transmission from a device, and it maintains those properties over a really broad range of wavelengths. That's very surprising if we have in mind the picture of this conventional guided mode resonance filter. Well, if we look at the transmission reflection on a log scale, here we can actually see what's happening. We look at our transmission curve and we see multiple dips. This means we actually have multiple resonances that have come in close proximity, and they're working together to give us one broad transmission reflection response. So before I describe this multiple resonance thing as bad, but in fact we can use this, and people are becoming very good at designing multiply resonant GMRs to get an overall broad frequency response. And folks are also doing this, we are doing this, combining multiple resonances to also make it wide field of view. So our guided mode resonance filter can accept waves over even just a 40-degree swing of angles, and that's huge. Typically guided mode resonance filters has to be less than a degree. But now we've designed devices that work the same way over a 40-degree field of view. That's pretty amazing. Due to the birefringence in the grating, they're also sensitive to polarization. What can we do about that? Well, some people have found special cases where we have a ruled grating that should have a different polarization response, but there's a special angle of incidence with everything special such that the two polarizations coincidentally have a resonance at the same wavelength, and we can make something polarization independent that way. Maybe an easier way is to get away from gratings that are birefringent and go to something that's more like a crossed grating. So square arrays and hexagonal arrays will give us a polarization independent device. The other thing we can do is incorporate additional anisotropy to compensate for the birefringence produced by the grating and end up with something that is polarization independent, if it is possible to introduce that anisotropy. And maybe there's more ways. The cross grating way is probably the most common way to make polarization independent guided mode resonance filters. This slide takes us back to an earlier problem we discussed, where we were talking about how many periods is needed in a guided mode resonance filter. The external wave couples into a guided mode. That guided mode zings along and it sees the grating, so it slowly leaks from the guide, but it needs to leak all the way out in order to interfere with the applied wave. So the question is, how long does it need? How wide do these things need to be? And the answer is usually several hundred periods, at least many dozens. Well, here's one way around that. Suppose we have just a few periods. I think I'm showing 7 periods here. We add maybe a little spacer region and then a reflector. And we adjust these spacer regions and the whole length of this cavity such that the round trip phase of a guided mode would be an integer multiple of 2 pi. If this weren't the case, it would interfere with itself and escape. But by putting these reflections here, we are essentially making a guided mode resonance filter that is infinitely long. And in fact, we built this and demonstrated this. Without the reflectors in place, if we look at the transmission through the device, we pretty much just see a flat line. With the mirrors in place, we suddenly see a resonance at 1.5 gigahertz. So this really does confirm that this works. One surprising thing that we found with these spacer regions, we originally included them thinking we would need to adjust them to somehow ensure that this is an integer multiple of 2 pi, the round trip. But what we found was that pretty much anything made it a resonant device, and by controlling the spacer region, we were able to tune where that resonance was. That was a bit of a surprising conclusion. But in fact, we can make these things work with much fewer periods. In fact, one of my students designed a 1-period GMR. So imagine sticking 1 period of a GMR in a waveguide and producing a filter response. So that was kind of neat. Now let's step through some simple applications of these. And I can only just hit on the tip of the iceberg here, but I think it will give you a feel of all the different ways that folks are using these. Our research, we're using guided mode resonance filters to filter very, very high power microwaves. if you've ever put metal in your microwave oven at home and you see sparks, that's what happens at a few kilowatts. Well, imagine what would happen at a few megawatts or gigawatts. So we're adopting an all dielectric approach. We're using guided mode resonance filters to do that, and we've already demonstrated some really, really high power surfaces. And we've also put engineering into these to broaden their bandwidth and their field of view all at the same time. So that I know of, here at UTEP, we have the world's highest power frequency selective surface. And we talked about this application before, wavelength selective mirrors for locking lasers. Lasers have a resonant cavity where there's photons bouncing back and forth. And the mirrors at either end, if we could make them be filters, then we could laze over a narrower line width. So guided mode resonance filters, we can make them arbitrarily narrow. They're excellent, excellent choices for locking lasers. A lot of folks, including Magnuson's group, by the way, he's probably the most published author in guided mode resonance filters. I don't think we can think of a guided mode resonance filter without thinking of Robert Magnuson. Some of the work he's doing now is making sensors out of guided mode resonance filters. One problem with guided mode resonance filters is that they're very sensitive to everything, to their material properties, to their structural dimensions, which makes them great for sensors. We can attach chemistry to these things that detect different chemicals or organic compounds, and they work very well for that. We can also exploit their sensitivity and make tunable filters. So we can use heat to tune the spectral response of a guided mode resonance filter. Folks are using these, they shine a pulse through a guided mode resonance filter, and they can use that to delay or otherwise shape the pulse. Due to the birefringence in the grating, these things can be made very sensitive to polarization. In fact, we can make polarization splitters out of them. And that concludes the guided mode resonance filter discussion.